have a data file which is called Spotify. Consider this like a Pac-Man. We can get so close to Spotify's recommendation algorithm. Hello everyone, in this video we will see some popular clustering algorithms that we can also apply in Python. Also, the other thing I would like to show today is how we can capture Spotify's recommendation algorithm. Spotify is running a more complex algorithm, but we will apply some simple algorithms in this video and we will see if we can get close to what Spotify is recommending us. The algorithms we are going to see in this lecture are centroid-based clustering algorithms. We will see only two of them, k-means and mean shift. Density-based clustering algorithms, we will only cover dbscan, and we are going to see some hierarchical clustering, and we will observe agglomerative clustering. Just as a summary, we are going to go over all these algorithms quickly. So as you can see in figure A, this is our data set, and we are assigning random centroids. We are assigning some random centroids. These are the red and blue dots, and then we are assigning nodes to these centroids based on the distance. For red nodes, this red centroid is closest, that's why we label them as red. So for the nodes over here, the blue centroid is the closest, that's why they were labeled as blue cluster or blue group. And then we recalculated the centroids based on the coordinates. We update the groups. For example, right now these red ones are not red anymore because they're closer to this new centroid. This is, as you can see in F, we updated the positions of the centroids again. There isn't any node that wants to change their cluster, so the algorithm is ended. The difference in mean shift clustering, instead of defining number of clusters, we define window like bandwidth, and we place this window on a data point. And then we calculate the mean for all the points in the window, and then we shift this window. And then this window is moved until we reach a convergence. For the rest of the nodes who doesn't belong to any group, we assign new windows and we try to cover every point. First two algorithms were based on distance. We estimated these clusterings based on the distance among data points, but in density-based algorithm, we try to capture density, and we place a window or a circle, and then we check number of units inside this window. In dbscan algorithm, we have two different parameters. One of them is the unit of a circle, and the other one is how many data points at least we have to have in this circle. This is the concept that forms a cluster. Let's say we place this window over here and we have all the requirements. We have a core point, and then within the epsilon unit we have for example, we have 4 data points. For each border point we draw the same circle again, and we're checking the number of points. It's 4. These are also included in this cluster. So as you can see, if we draw one more circle over here for this point, there isn't any point that we can include, so the clustering stops over here. The same thing for here. Consider this like a Pac-Man. Pac-Man starts to eat, and whenever whenever it couldn't find anything to eat within this distance, it stops. And all these points that doesn't belong to a cluster called noise. While centroid-based algorithm cannot capture the density like in figure 1, DBS-CAN algorithm can capture the density. So this shape looks so much better. The fourth one is agglomerative clustering. Consider another example with a lot of students and their scores. We have 5 different students and we can see their scores, and we calculate the difference, the absolute value of the differences. We find the shortest value in this 5 by 5 matrix, which is 3. It means that student 1 and student 2 are closest pairs in this group, so we merge them. Now student 2 is in blue group. Now we update this distance matrix, and then we check the shortest distance again, which is 7, and it's between 3 and 5, and 3 and 5 is going to be merged, and they are both green right now. We will update our matrix again. We will check the distances. So I'm just skipping quickly over here, and then at the end we will merge all of the nodes in the same group. So over here, for example, first we combined 1 and 2, base distance was 3, and then we combined 3 and 5, distance was 7, and we combined 1, 2, and 4, the distance was 10, and at the end we combined all of them together when distance between these two clusters were 15. Here we define a threshold. Right now we say, let's say the threshold is 12, and it is cutting 2 lines over here. It means that we have 2 clusters. This is the first one and that's the second one. If the threshold was over here, we were going to have 1, 2, 3 different clusters. In this video, we are going to use pandas, matplotlib library, sklearn cluster module. We are going to import k-means, mean-shift, DBS-CAN, agglomerative clustering. These are the methods we talked about just a minute ago. And before applying those, I'm going to show you how to preprocess our data. We are going to apply standard scaler. And over here, we have some metrics that I would like to show you. One of them is silhouette score. The other one is Davies built-in score. We are going to apply principal component analysis. We have a data file which is called Spotify, and let me show you how it looks like. These are the songs in top 50 from year 2010 to 2019 in Spotify. What we want to make is to group these songs together with our clustering algorithms and to see the different groups and the similarity between some songs. Also, I'm really curious about if we can capture the clustering algorithm behind Spotify's recommendation system. Let's see how close we can go with some simple methods over here. So this is how my Spotify file looks like. We have the song title, artist, top genre, the year they're published, and all these levels such as like BPM, energy level, dance level, and acoustic level, and pop level, duration, and bunch of other levels. I don't even know what they are. Just want to see how my data looks like. So we have, in total, we have 14 columns. We have 603 different songs. And as you can see, right now, I think genre is important in clustering. So I would like to convert this top genre column to some integer numbers. For this, I'm applying label encoder. Label encoder came with the scalar preprocessing. So when I apply that, now top genre is an integer number, and let's see what happened. For each different genre, it gave me an integer number. Let's continue. So scaling in clustering algorithms are really important. Why? Because we are checking the distance. So the difference between, so some numbers are super small, but some numbers are so big. Since we calculate the distance based on the unit, we have to transform those data sets and they should look like comparable with each other. That's why we applied standard scalars. Standard scalar transforms them, each column, so that each column has a mean 0 and a standard deviation 1, like standard normal distribution. For this analysis, I am choosing all of the columns and I would like to transform them into a normally distributed values. As you can see, the values are close to each other right now because we are going to use some distance-based algorithm. So we want every column to be comparable within each other. The next step is principal component analysis. What does principal component analysis do? As you can see, we have a lot of columns over here. 1, 2, 3, and even I cannot count it. Let me count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Principal component analysis is going to reduce the dimensionality of my data set. It's going to project these 12 columns into 2 columns. So it uses different methodologies, such as checking the orthogonality of the columns and etc. That's another long topic, so we are not covering it over here. We are just going to use it in our code. We want only 2 columns. For also, this is appropriate to use to visualize our data. We are going to transform the scale data we had in the previous step, and we are this is now the transformed data is going to be X principal. We are converting X principal to a data frame, and we are assigning some headers for these 2 columns. I don't like to type X principal all the time, so I want to use X again. So I'm assigning X principal to variable X. Let's run this. If you want to see how it looks like, now these columns are totally different what we have previously. We are going to apply k-means, mean shift, db scan, and agglomerative clustering, and this is that easy. Let's start with k-means. I would like to create a k-means object with number of clusters is 2. I would like to fit my x value, and I would like to predict these groupings. For example, these are the songs and their groups, their clusters as 0 and 1. I just want to show you a quick way. Instead of using this, that's also possible. K-means and clusters is equal to 2 dot fit and predict. So this one line covers all these 3 rows over here, and it's the same thing. What I want to do is I would like to, in my data, I would like to create another column which is called k-means, km predictions, and I will assign these values into this column. So let me show you how data km pred looks like. All of the songs and their groups. As I told you before, I'm gonna use this short way instead of typing all these rows. So let's say number of clusters is 2. Bandwidth, I'm just put a random bandwidth over here. If you don't type anything, it has its own estimator inside. Which is here. You can either trust that, and if you don't like the shape of your clusters at the end, you can define this on your own. So for the same thing, DBS can always has a default unit which is 0.5. You can use that, or you can type this value on your own. So for agglomerative clustering, you again specify the number of clusters you would like to have, and the rest is same old. So this is my first file, and I put all these predictions over here. These are the groups they belong. For example, these songs over here are grouped together. For each methodology, I would like to draw some figures. For example, this is k-means, this is mean shift, this is DBS can, and this is agglomerative clustering. I would like to check their silhouette score and the Davis building score. Silhouette score is estimated by considering the idea of how these clusters looks like. They should be as separated as possible, so it means that this score is gonna be 1, and higher the silhouette score is better the clustering, and the Davis building score is another metric that considers the variance. So lower the Davis building score is better the algorithm. Let's run this. Alright, this is the lowest Davis building score, and again this is the highest silhouette score, which is mean shift. Let's go check our So mean shift couldn't separate all these things, all these songs. They look so similar to each other because maybe the top 50 song of each year has a lot of similarity. So for k-means, I'm changing the number of clusters ranging from 2 to 10. 10 is not included, so it's going to be at most 9. So when we run this, so we're going to pick highest silhouette score, which is this one, but we need to pick lowest Davis-Billings score, which is over here 8. If we check agglomerative clustering, again we define number of clusters we want to see. Highest the silhouette score is the first one. The lowest the Davis-Billings score, again 8. For mean shift and DBS can, we need bandwidth. For mean shift we need the radius. For DBS can, so I'm importing numpy, and then we can create an array with different numbers starting from 0.5 to 1.1 with an increment 0.1. Silhouette score is the higher, is the best. Davis-Billings score is the lowest, is the best. So the lowest Davis-Billings score, again, the first one. And the highest silhouette score is again this one. But if we compare, for example, the previous one, k-means had the better silhouette score, 45. And Davis-Billings score is 76, but this one has, if we compare those methodologies based on Davis-Billings score, mean shift has a better one. So when we check DBS can, we are defining radius with the numbers starting from 0.5 to 1.1 with an increment 0.1. Silhouette score is the highest, the best, the last one, and Davis-Billings score is the lowest, the best is this one. So when I pick EPS as 1.1, it gives me the best clusters, best number of clusters. Other thing I want to do, I think the artist is important. So let's encode the artist with label encoding. That's artist over here. All right, cool. So artist is now an integer, and then instead of starting from top genre, I can start from artist. And what I want is only 2 columns that represents all of the columns. I can skip that process. Let's see how everything looks like. Wow, the data looks like, you can see it's more separable. I love this. It's more separable when we included artists. Artists are really important. Let's see the silhouette scores and Davis-Billings scores. Highest the silhouette score is this one. Lowest the Davis-Billings score is this one. Now I would like to see what is the best number of clusters for us. Highest the Davis-Billings score, highest the silhouette score, lowest the Davis-Billings score. Sounds good. For agglomerative, highest the silhouette score, lowest the Davis-Billings score is again 2. Number of clusters 2. So mean shift takes a lot of time. Highest silhouette score is this one, and no, it's coming over here. Highest the silhouette score, but lowest Davis building is this one. Alright, for DBS scan, highest silhouette score is this. David building is over here. So I remember I saw better David building score. So let's go with number of clusters 2 for both for k-means and this one. And let's set bandwidth 1 because it gave us a better score. All right. I love that. It's so much separable. These are the outliers. This is DBS scan. This is agglomerative. How my data looks like. All right. At least we have all of them. At least we have a consistency. Now I'm choosing all of my songs from cluster 0. All right. So all of these songs are in cluster 0. So I want to see the Spotify predictions are also in cluster 0. All right. So Spotify recommendations for all these songs are Waiting for Love, Burn, Uptown Funk, Something Just Like This, What Do You Mean, and Jim Lovin feat. And Jim Lovin. The songs I chosen are in this list. Also, Only Burn, Uptown Funk, What Do You Mean, and Something Just Like This are in top 50 list. Then I will create another index list for recommendations. Let's say, okay. Let's see the cluster we made is similar to the cluster Spotify makes for us, okay? So over here, rec, data ilog, in this index list, recommendations, and I would like to see if all is R0, it means that we captured it. Okay, I didn't run this. Let's run this. If all is 0, it means that yes, that's what we want to see. The Spotify predictions. Spotify gives me recommendations from exactly the same cluster we created with k-means and number of clusters too. Spotify recommendation algorithm looks like something complex, but even with k-means we can capture it. We can create a group of songs that are similar to the songs that are similar to songs we picked. So I picked some songs from group 0, and then recommendations, Spotify showing me were these songs, and then all of the songs belong to group 0. So not every song, for example, Waiting for Love or Jimmy Lovin, these were not in even my data set, so I cannot group them because I don't have the information of these songs. I know it's a very complex algorithm is running behind all these recommendation system. Recommendations Spotify is choosing for me is coming from this list. So even with a simple clustering algorithm, we can get so close to Spotify's recommendation algorithm. That's all for today, and hope you understand it. Hope you enjoyed with this video. I love you all, and all I want is just for you to improve yourself, learn better skills in this course, and hope to see you after spring break. Enjoy your spring break.
The work has been done and the buzz is gone, baby, I'm on my